Let us now look at the complex plane or the Argon plane. Complex numbers can be shown geometrically on a complex plane, which is also known as the Argon plane. The real part of the number is represented on the horizontal axis called the real axis, while the imaginary part is represented on the vertical axis called the imaginary axis. Recall that any complex number can be written as a plus bi, where a is the real part and bi gives us the imaginary part. Let's try to write these numbers and plot them on the Argon plane. Minus 3 can be written as minus 3 plus 0i because there is no imaginary part. In terms of coordinates, this can be written as minus 3, 0, and we plot it on our plane. This is the point minus 3, 0. Next, minus 4i can be written as 0, minus 4i. Here there is no real part, so the corresponding point is 0, negative 4, and plotted on the plane, the point is here. The next corresponding point is 3, 2, so the real part comes first, followed by the imaginary part. So 3, 2 is here, 1, 2, 3, 2. And the last one we have 2, negative 2, which is here, 1, 2, negative 2. Let us now look at the absolute value or modulus of a complex number. The absolute value or modulus of a complex number is the distance from the origin to the point. This can be found by using the Pythagoras theorem. The absolute value of a complex number z equals a plus bi is given by absolute value of z equals square root of a square plus b square. Let us now look at an example. Graph each number in the complex plane and find its modulus. The first number is z equals 4 plus 3i. Writing it in the coordinate form, this can be written as 4, 3. So we draw our complex plane. This is the real axis and this is the imaginary axis. And we plot our point 4, 3. To find the absolute value, we use the Pythagoras theorem and substitute the values of a and b. So square root of a square plus b square on simplification gives us 5. Let's look at the second one. Here we want to graph the number in the complex plane and find its modulus again. So again, when we write it in the form of coordinates, this is minus 2, minus 1. Again, we draw the complex plane, mark our real axis and the imaginary axis, and plot the point. To find the absolute value, we again use the same formula, square root of a square plus b square, substitute the values of a and b, and find the final answer. It's your turn now. You need to graph each number in the complex plane and find its modulus. Pause the video and resume when you're ready. Let us now check our answers. For the A part, AB is 5, 2. This is the graph and this is the modulus. For the B part, A, B is negative 3, 4. This is the graph and this is the modulus. Hope you got both the answers correct. Look what is happening here. It looks like the real and the imaginary parts are having an argument. But this is not what we mean by the argument of a complex number. The argument of a complex number is the angle the line makes with the positive x-axis. For any complex number z equals a plus bi, argument of z is given by theta, and this theta is equal to tan inverse of b over a, where the value of theta lies between minus pi and pi. It is important that you sketch a diagram before working out the argument. Use the formula for the modulus and argument of a complex number to calculate the modulus and argument of the following complex numbers. Remember, it helps to draw a diagram. Pause the video and resume when you're ready. Let's now check our answers. Well done if you got both the answers correct. What is the polar form of a complex number? The polar or trigonometric form of the complex number z equals a plus bi is z equals r times cos theta plus I sin theta, where r is the absolute value of z and is given by square root of a square plus b square. A is equal to r times cos theta, b equals r times sin theta, and the argument theta is equal to tan inverse of b over a for a bigger than 0, or theta equals tan inverse b over a plus pi for a less than 0. Let us now solve an example. Here we need to express the complex number -6 plus 8i in polar form. So to do this, we'll find the modulus r and argument theta. We substitute the values of a and b in the formula for r and theta. Note that here a is negative, so the formula for theta is tan inverse b over a plus pi. We substitute the values and get the values of r to be 10 and theta to be about 2.21. So the polar form of -6 plus 8i is about 10 cos 2.21 plus I sin 2.21. Let us now look at another example. Here we need to graph z equals 3 times cos pi by 6 plus I sin pi by 6 on a polar grid and then express it in the rectangular form. So here we are given a complex number in the polar form and we will write it in the rectangular form. Here if you note, the value of r is 3 and theta is pi by 6. So we plot the polar points 3, pi by 6 on the graph. So here we have 3 and pi by 6. To express the number in rectangular form, we evaluate the trigonometric values and then simplify. So this is the complex number in the polar form. We substitute the values of cos pi by 6 and sin pi by 6 and simplify. So this is the expression for this complex number in rectangular form. It's your turn now. Pause the video and resume when you're ready. Let us now check the answers. Well done if you got both the answers correct.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below and send us a message now. Okay, with that said, let's get back to our lesson.
And quotient of complex numbers in polar form. Suppose we are given two complex numbers z1, which is r1 cos theta 1 plus I sin theta 1, and z2, which is r2 cos theta 2 plus I sin theta 2. Then we have the product formula where we multiply the two complex numbers z1 times z2. This becomes equal to r1 times r2 and cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. For dividing the complex numbers, we use the quotient formula, which states that z1 divided by z2 is given by r1 by r2 times cos theta 1 minus theta 2 plus I sin theta 1 minus theta 2. Notice when multiplying the complex numbers, you multiply the moduli and add the arguments. When dividing, you divide the moduli and subtract the arguments. Let's look at an example. Here we want to find the product of two complex numbers given in polar form. So our given complex numbers are 2 times cos 5 pi by 3 plus I sin 5 pi by 3 times 4 times cos pi by 6 plus I sin pi by 6. Then we need to express the product in rectangular form. So this is our original expression. Remember, to multiply two complex numbers in polar form, we multiply the modulus and add the arguments. So here we do 2 times 4 and add the arguments. So cos of 5 pi by 3 plus pi by 6 plus I sin 5 pi by 3 plus pi by 6. This on simplification gives us 8 cos 11 pi by 6 plus I sin 11 pi by 6. Now let's find the rectangular form of this product. This is our original equation in polar form. We substitute the values for cos 11 pi by 6 and sin 11 pi by 6 and apply the distributive property. So we get the product in the rectangular form. Let us now look at a real-world example where we require to find the quotient of complex numbers in polar form. If a circuit has a voltage E of 100 volts and an impedance Z of 4 minus 3J ohms, find the current I in the circuit in rectangular form, and we use the formula E equals I times Z. So to begin with, we express each number in the polar form. So here we can write 100 as 100 plus 0I, which is our first complex number, and impedance is already written in the correct form, 4 minus 3J. So 100 we can write as 100 cos 0 plus j sin 0. Again, we found the r by using the formula square root of a square plus b square. And from here we can see a is 100 and b is 0. Similarly, we found theta by using tan inverse of b by a, which is 0. Similarly, we write 4 minus 3j in polar form. Here a is 4 and b is negative 3. So again we find the values of r and theta and write 4 minus 3j in the polar form. Next, we want to find the current I. So we rearrange the terms of this equation to find I. Next, we substitute for E and Z. So E is 100 cos 0 plus j sin 0 and Z is 5 cos negative 0.64 plus j sin negative 0.64. Now from the quotient formula, we know that we divide the moduli and we subtract the argument. So we get 100 divided by 5 times cos 0 minus 0.64 plus j sine 0 minus 0.64. So our simplified expression becomes I equals 20 cos 0.64 plus j sine 0.64. So we have got an expression for current in the polar form. Now we want to convert this current to rectangular form. For that, we simply evaluate cos 0.64, sine 0.64, substitute the values and use the distributive property. So the current is about 16.04 plus 11.94 J amperes. It's your turn now. Pause the video and resume when you're ready with the answers. Let's check the answer. For the first question, the correct answer is part C, and for the second question, the correct answer is part B. We now move on to our next key concept, the de Moivre's theorem. The theorem states that if the polar form of a complex number is z equals r times cos theta plus I sin theta, then for positive integers n, z to the power n equals r times cos theta plus I sin theta whole to the power n, or r to the power n times cos n theta plus I sin n theta. Let us now see an example where we use de Moivre's theorem. We want to find the fourth power of this complex number 3 plus 3 root 3i and express it in rectangular form. So to begin with, we first write this complex number in polar form. So we calculate the value of r and theta. Here a is 3 and b is 3 root 3. So we substitute the values and simplify, and we get r equals 6 and theta equals pi by 3. So the polar form of 3 plus 3 root 3i is given by 6 times cos pi by 3 plus I sin pi by 3. Now we use de Moivre's theorem to find the fourth power. So in place of 3 plus root 3i, we write the polar form, which is 6 cos pi by 3 plus I sin pi by 3 whole to the power 4. Now we use the de Moivre's theorem, so we get 6 power 4 times cos 4 pi by 3 plus I sin 4 pi by 3. Further, we simplify and evaluate, and on further simplification, we get the fourth power of 3 plus 3 root 3i equals minus 648 minus 648 root 3i. It's your turn now. Pause the video and resume when you're ready. Let us now look at the correct answer. The correct answer is option A. Let us now look at the next key concept, which is about finding the distinct roots of a complex number. For a positive integer p, the complex number r cos theta plus I sin theta has p distinct pth roots. They are found by r to the power 1 by p times cos theta plus 2n pi over p plus I sin theta plus 2n pi over p, where n is from 0, 1, 2 till p minus 1. Let us now find the pth roots of unity. For example, we want to find the fifth roots of unity. Here, unity stands for the number 1, which we can write as 1 plus 0i. We write 1 in the polar form, So r is square root of a square plus b square. So a is 1 and b is 0. And theta is tan inverse of b by a, which is 0 by 1, which is again 0. So the polar form of 1 is 1 times cos 0 plus I sine 0. Now we write an expression for the fifth root. This is given by r to the power 1 by p. So r is 1 and p here is 5 because we want to find the fifth root. So r to the power 1 by p will be 1 to the power 1 by 5, which is 1. Cos of theta, which is 0. So 0 plus 2n pi over p. So p is again 5 plus I sine 0 plus 2n pi by 5, which on simplification gives us this expression. Now the values of n we would take from 0, 1, 2 up to 5 minus 1, which is 4. So the values will be 0, 1, 2, 3, 4. To find the first root, we put n equal to 0. So if we substitute n equal to 0, we get cos 0 plus I sine 0, which is 1. This is the first root. Now if you note that the modulus of each complex number is 1 and the arguments that are found, they vary by 2 pi by 5. So we can calculate the remaining roots by adding 2 pi by 5 to each previous theta. So for the second root, we just add 2 pi by 5 to 0 and get the second root. We get cos 2 pi by 5 plus I sine 2 pi by 5, which on simplification gives us this value. For the third root, we add 2 pi by 5 here. So we get 2 pi by 5 plus 2 pi by 5, which gives us 4 pi by 5. And we evaluate cos 4 pi by 5 plus I sine 4 pi by 5. For the fourth root, we again add 2 pi by 5 and evaluate the expression. And for the fifth root, we again add 2 pi by 5, evaluate and find the value for the fifth root. The last thing is to plot all the roots on the Argonne plane. So the first root is 1, 0. Next we have 0.31, 0.95, which is here. Next is negative 0.81, 0.59, which is here. The fourth root is negative 0.81, negative 0.59, which is here. And the fifth root is 0.31, comma, negative 0.95. It's your turn now. Pause the video and resume when you're ready with the answer. Let us now check the answer. The correct answer is option D.